Okay, so I've got 3 questions for you today. It shouldn't take very long. This is, again, on amplitude modulation. And then the next week, so we'll do more amplitude modulation, and then we'll do single sideband and vestigial sideband stuff the next week. So tutorial questions for next Monday and next Wednesday, those will be all fair game for your midterm. So I should be able to cover enough questions so that by the end of next Wednesday, if you study all those tutorial questions and if you take a look at perhaps some of the past midterms, for example, with their have full solutions there, then you should be in pretty good shape for the midterm. Okay? All right, so here's the first question. This is the first part. There's actually 6 parts to this question, but I'm only showing the first couple of parts here. So we've got an AM signal, okay, and we know that M of t is real valued. So what it means by real value, this means that the spectrum is symmetric, which is nice. Spectrum is symmetric. And notice that the spectrum, they only show 1/2, which makes sense, because if it's symmetric, you don't need to show the negative half. So it's a real value modulating signal, and we want to, so this is what the Fourier transform will look like of the AM signal, okay? So the next thing we have to do is we have to figure out what the carrier frequency is, what the carrier amplitude is, and what the original message is, as well as the modulation indices. So we have mu, and then mu plus and mu minus. Okay, so because it's real value, this is very important. So this means that if you were to take a vertical mirror and put it at at a certain point, if you take a look at the left and the right side, they should match up, right? So you probably agree with me that the carrier frequency is probably this guy over here, right? Just by observation, right? So let's do that. So f of c here. So f of c is equal to 50 kilohertz. Okay? All right. So the amplitude. Okay, so if you remember what the transform was for the AM signal, right? So I'm just going to do this in frequency for now. It was what? It was half. Not half. Was it half? Yeah, it was half. I think it was. I'm pretty sure it was half. Yeah, half. Was it half? I'm trying to remember. Yeah, it was half. So half. We have delta f minus fc plus delta f plus fc. Okay, and then we also have the message signal itself. So we have 1/2 m of f minus fc and 1/2 m of m plus. Okay, so we have 2 impulses that are plus minus fc that are scaled by 1/2. Okay, so we have it's not 1/2. It's actually a over 2. Sorry, it's ac over 2. Okay, so if we see here that the impulse height is 2. Right, so this here would be AC over 2. So the original height would simply be 4, right? Because if AC over 2 is equal to 2, then it would just be equal to 4 instead. That would be the actual height. Okay, so therefore, AC is equal to 2 times 2, which is 4, right? Because this here already scales the impulse by 1/2. That's what's being displayed. So to get the original amplitude back, I just multiply by 2. Okay? Now, what's the original message signal? So the original message signal would be, okay, so let's draw it out. So it looks like this for now. So M of F. Remember, because we're using 50 kilohertz as the mirror, basically what I'm going to do is I'm going to shift everything back by 50, right? So in this case, we're going to have plus minus 2 and plus minus 4. So we're going to have, let me see here. So it's 2 and 4. Sorry. So 1. I'm not going to draw the heights yet on purpose, and I'll show you why. Okay, so we have 2 impulses, okay? So we have minus 4, minus 2, 2, and 4, and this is in kilohertz. Okay, so if you remember what the Fourier transform for the cosine was, right? There are basically 2 impulses. So we have 1/2 delta f minus f0 plus 1/2 delta f plus f0. Okay, so we have 2 impulses that are scaled by 1/2, and then in general, if we have some value of a, this becomes a over 2. Okay, so we have 2 values that are scaled by 1/2, and then additionally we have this factor of 1/2 that scales everything. So what's happening here is that our impulses are actually divided by 4. One time for the 1/2, okay, and the other time for this. So what we have to do now is we simply have to take our impulses and multiply each of them by 4. So 1/4 becomes 1 and 1/2 becomes 2. So we get 1 and 2. Okay, so do you understand why I multiply this by 4? It's because the original cosine, the impulses, they already have a scale of a half. And then you're scaling by half one more time when you're doing the amplitude modulation. This is half times m, right? And m was already scaled by a half. So a half times a half is 1/4. That's why you have to multiply it by 4, because you have to multiply by 2 to get rid of the scale that's done by the modulation, and then you have to multiply by 2 again to get the original impulse back, right? So you have to multiply by 4. So the factor of 4 is due to modulation and the fact that you have the original cosine as well. So let me just write that down. So therefore, we multiply, so this is 1/2 times 4, and this is 1/2 times, so not 1/2 times, this is 1/4 times 4. We multiply by 4, right? Because, let's see here, because of scaling by half twice. Okay, so actually no, this is not the original. So this is actually, I'm sorry, this is actually just 2. It's not 2 and 1, but the original one is 2 and 1. So let me just correct this quickly. Okay, so the original spectrum is simply multiplied by 2, but if you want to get the original wave back, then you have to multiply by 2 again. So I'm sorry, this is actually 1.5. This is the actual spectrum. Okay, so we multiply by 2 because of the scaling by a half due to modulation. Okay, sorry. Okay, so our Fourier transform, so this transform now, so this message signal, okay, it's not multiplying by 4, it's multiplying by 2 first. So we have delta f minus 4 plus delta f plus 4, okay, and then plus a half delta f minus 2, and then a half delta f plus 2. Okay. Now we want to figure out what the original message is. This is in terms of frequency. Okay, so m of t, okay, well, these two together make what? 2 cosine 2 pi 4t, or 8, right? And then this here is what? Cos of 2 pi 2t. Okay, so this becomes 2 cosine 8 pi plus cosine 4 pi. Okay, so when you draw the original spectrum, you scale by a half, right, because of the modulation, due to the modulation, so it's this guy over here. Okay, so then this would be what the spectrum looks like originally, and then if you want to go to the original message signal, you have to multiply by 2 because of this guy over here, right? So you multiply by 2 twice, so twice to go to the original spectrum, and then twice again so that you get the original, what the original message signal was. Okay? And that will be the message signal there. Okay, any questions here? So it's, pretty straightforward, I think, at least for part A. Okay, part B. We have to figure out what the modulation indices are. So we have mu. There's 2 ways to do this. You can either do the maximum peak divided by the carrier frequency, okay? In this case, the maximum peak will be what? Well, the maximum peak is just simply 2 plus 1, right? Because when you'll get to a point where 2 of these peaks are going to match up, so you're going to have 2, and then the 1, so you get a 3. So 3, and then the carrier height was equal to 4, right? 3 over 4. Okay, there's another definition as well, right, where we can use A max minus A min divided by 2A, right? Actually, this is AC. Right? AC, yes. Thank you. Okay? So A max is equal to what? Right? It's equal to, let's see here. So we have max of AC plus m of t. Okay? So what we're doing here is when we add the carrier on top, what will be the largest value that we get? Okay? So this is 4, right? This means the largest value we're ever going to get is going to be 3. So we're going to get 4 plus 3, which is 7. Okay, the minimum is pretty much the same thing. So we're going to have the minimum value that we get when you add this with the carrier. Okay, so what's the minimum value we're going to get? So we're going to get to a point where, remember, this fluctuates between +2 and -2, and then the next one fluctuates between +1 and -1. So we're going to get to a point where it's going to go -2 subtract -1, right? So this is 4, and then this becomes -3, right? So we get 4 minus 3, which is 1. Okay, so if you want to calculate this, it's simply 7 minus 1 divided by 2 times 4, which is 6 over 8, which is 3 over 4. That's nice. The reason why this and this match, if you remember from the lectures from a couple days ago, is that the signal is symmetric. So if the signal is symmetric, then both of these definitions will match. And if they're symmetric, that means the positive and the negative index is also going to match as well. Okay, so let's calculate that just to be sure. Okay, so let's calculate the positive side. So we get mu plus is equal to A max subtract AC divided by AC. Okay, so in this case we got 7 minus 4 divided by 4, which is 3 over 4. That's good. Okay, and then let's take a look at what the negative side would be. So this would be AC subtract the minimum divided by the carrier again. So this becomes 7 subtract 1 divided by, let's see here, 7 subtract 1 divided by 4. Actually, no, it's not 7, sorry, it's 4. 4 subtract 1 divided by 4, which is 3 over 4. So all of these match, of course. Okay? This is because the signal is symmetric. If it wasn't, then none of these are going to match. Okay? So that actually makes sense. Okay. Good so far, right? Yes?
Could you explain what MFT, y and 3?
I'm sorry?
For MFT, y and 3?
F of t.
No, MFT.
M of t? Which one?
You try to find A max or A min?
Oh, the reason why is because, okay, so this fluctuates between plus minus 2, yeah? Okay, so it looks like this. So it's going to be at twice the frequency like this. Okay? And then we have this guy over here. It's going to go between plus minus, but it's going to fluctuate over time like that. Okay? You're going to get to a point where both of these peaks are going to match. In this case, it's over here. Right? So when you add these together, 2 plus 1 is 3. Right? You're going to get to a point where both of the peaks will coincide with each other, and then when you add them both up, it's just 2 plus 1, which is 3. And then you can do the same thing on the negative side as well. You get minus 2 minus 1 is minus 3. And that's where that comes in. Okay? Does that make sense? Okay. All right, let's do the next parts here. So, all right. Okay. A little bit of a mouthful, but totally fine, all right? C. Determine the average sideband power and the average carrier power and the average signal power, which is just adding them both up, right? So this is just PC plus P of S. Okay, and the power efficiency. Okay, so let's do that first. This is actually 2 questions in one, but let's actually split that up. Okay, so average sideband power. Actually, let's do the carrier power first. It's actually a lot easier to do. So the carrier power, okay, that's actually very simple. It's simply the okay. So I actually made a mistake in the previous class. I actually divided by 2 again, but you're not supposed to do that. So it's just the carrier squared divided by 2. So the carrier was equal to what? It was 4, right? So 4 squared divided by 2 is just, what's 16 over 2, which is 8. Also, I'd like to point out that its power values are normalized to unity. So what this means is that the load is simply 1 ohm, and that's what it is. Okay? In general, if you did not have a unit resistor, then what you would have to do is you'd have to apply an additional R here. But in this case, this is just equal to 1. But so it's superfluous here, but that's what you do. So that would be the power of the carrier. The power of the sideband is actually very simple. Okay? What you simply have to do here is you have to power carrier, power sideband. Yeah, that's what I did. Yeah. So power the sidebands. So basically, we have, what was it? The original message signal was 2 cos, and then we have, sorry, it's not, I'm sorry, it's not 8 pi, it's 8,000 pi. So it's actually, so this is actually 2k. Sorry about that, because this is in kilohertz, right? So this is actually 4,000. Sorry, this is 4,000, 4,000. It's in kilohertz, I forgot. So we have 2,000. Okay, it's not 2, it's 2,000 because it's in kilohertz. Okay, so sorry about that. So because the impulse here is in kilohertz, so this is minus 4,000 plus 4,000, and this is minus 2,000 plus 2,000. I forgot it's in kilohertz. So it's not plus minus 4, it's plus minus 4,000. Forgot about that. Okay? Okay. So, all right, so 2 cosine, and this is 8,000 pi t. and then plus cos 4,000, yeah? Okay, so let's call this P of 1 and let's call this P of 2. So you just have to add up these powers together, right? So let me see here. So it's P, so it's actually, so let me see here. So power is actually, in this case you do divide by 2. So the carrier, you don't have to do that. In the message signal you do. So if I want to figure out what this is, it's actually very simple. You're just adding up the two things together. So remember, this becomes 2 squared divided by 2, and then plus 1 squared divided by 2, which is what? It's 5 over 2. Okay? So in this case, we get 5 over 2, and then divided by 2 again, we get 5 over 4. All right, so now that's it. If you want the total power, you're just simply adding up the carrier and the sideband together, so you get 5 over 4 plus 8, which is 37 over 4. Right, because let me see here. Because this is 8 times 4, which is 32. You want to make this a common denominator, so you get 37 over 4. Now, if you want to figure what the efficiency, it's very simple. So it's the ratio of the sidebands with respect to the carrier and the sidebands, and that's just equal to the total. So this is just the total. So in this case, we get power sidebands. So we get 5 over 4. Right, so this guy over here divided by 37 over 4. These 4's cancel, so you get 5 over 37. As the efficiency. Okay, so I'm not quite sure what that is, but it's pretty bad. So 5 over whatever that is in percentage. Okay, so that would be, let me see here. So I think that's it. All right, for that part. So I got the efficiency, I got the carrier power, got the average signal power. Now you are asked to improve the power efficiency. How exactly would you do this? And are there any limits to how far you can actually get? Okay, well that's actually pretty simple. So remember that the condition, so remember the condition to make this possible to use an envelope detector, you have to make sure that the modulation index is between 0 and 1. Okay? So if you want to make this between 0 and 1, and then you want to make n as, or not, the efficiency as large as possible. Okay? So how exactly do you do that? Well, what you have to do here is this means that you have to make the power as large as possible for the sidebands. So how do you do that? Well, what you can do is you can just apply some sort of gain to the original signal. The carrier you can't change, that stays the same. But if you want to increase the efficiency, well, what you can do is you just have to make the power of the sidebands large. And how do you make the power of the sidebands large? What you can do is you can increase the amplitude. So when you increase the amplitude, the power should eventually increase as well. Okay? So therefore, increase, no, not increase, but increase gain for input as large as possible, to be as large as possible, for input to be as large as possible. Okay, up until the efficiency is equal to 1, and that's as far as you can go. As soon as you make the efficiency larger, that means you have to use coherent detection, which is probably not what you want. You want to be able to just use an envelope detector. Okay, so increase gain for input to be as large as possible up until the mu is equal to 1. So what you'll do is you'll make a new signal, which is just taking some gain k and multiplying it by your message. So you're going to take this instead. So that's what you're going to do, where k is some number. So that's what you'd actually do. All right? So the moral of the story is if you want to make the efficiency better, you want to increase the amplitude of your message up to the point where the modulation index is equal to 1, which means that you can use an envelope detector for that particular situation. And then once you pass that point, then you can't do that anymore. Okay, so if m of t in the amplitude modulated signal is to be replaced by some gain multiplied message where it's a real number, what we need to do is you have to figure out what the largest value k is going to be so that you're able to recover your message using an envelope detector. And then also determine the power efficiency as well. Okay, that's totally fine. Okay? So that's actually quite simple to do. So what you have to do in this case, because it's symmetric, we can use both definitions of mu. So what we're saying here is that, remember, the efficiency is equal to the largest peak divided by the carrier. Okay? I want to make sure that the upper limit which is equal to 1. So that means that at mu is equal to 1, that'll be the best efficiency possible. So I have to make 1 equal, and then the largest peak is going to be what? It's going to be k of, actually, so m of t here. So if you remember what the original message peak was, right? Originally, this was equal to 3 from m of t, okay? So if I apply some gain to it, then what will happen is that the largest peak will be 3 times k, right? If the largest peak is 3, if I add a k factor to it, then the largest peak will be simply 3 times k. And the carrier amplitude is 4. So if I solve for this, k would be simply 4 over 3. Okay? So that's how I would do it. So if m of p is equal to 3, therefore k m of t, right, the max here, would be 3k. Makes sense, right? Because if the original message, if the maximum was 3, if I apply some gain to it, then the max would be 3 times k, right? You're just adding a gain to it. So this is what the constant would be, which would simply be 4 over 3. That's how I would do it. Okay? And then what we're going to do now is we're going to figure out what the efficiency is. Well, remember, you're not changing the carrier, so the power of the carrier is going to be exactly the same. Okay? So the power of the carrier is unchanged. We don't change the amplitude of the carrier. So this is simply equal to 8. All right? But the power of the sidebands, it's going to be equal to what? So remember, this becomes, so if you remember what the original power was, right? So power originally was, let me see here. So it was, no, actually, let me do it this way. So our message signal now, okay, is equal to k, and then we had 2 cos 8,000 pi t plus cos 4,000 pi t. Okay? So what'll happen is that I have to bring this inside, okay? So this becomes 2k cos and then plus k cos. So if I find the power of this now, okay, so what is the time varying average here? So this becomes what? 2k squared divided by 2 plus k squared divided by 2. So this becomes 5k squared divided by 2. Okay? And if I want to figure out what the power of the sideband is now, it's simply 5k squared divided by 2, which is 5k squared over 4. Okay? Now if I want to figure out what the efficiency is, it's simply what? 5k squared divided by 4 divided by 5k squared divided by 4 plus 8. Okay? And then I know for a fact that k is equal to 4 over 3. So if you substitute this all in, okay, I'll let you do that math for yourself. If you actually substitute this all in, we actually get 5 over 23. Okay? So 5 over 23, and then compared to 5 over 37 originally. Okay? So notice that 5 over 23 is larger than 5 over 37, which is great. So this actually proves the fact that if you change the amplitude of your message, you will get better efficiency, but it'll be slightly better. But no, this I believe is about 22%, and the other is about 14%. So this is roughly 22%, and this is roughly 14%. So it, even though there's about an 8% increase, it's not, it's not something to write home about, I guess. Okay, so that's what happens when you change the amplitude. All right, what's the last part? Okay. So assume that m of t is replaced by 2 times k, right? Design an appropriate demodulator such that the output will be m of t. Okay, so remember that k was the value that you would need to perform a envelope detection, right? If you go any further than k, what that means is that your envelope will go below the horizontal axis. So that means you're going to need a coherent detection algorithm now. So remember, k of m of t is the waveform that you have that will give you the best possible, not the best possible case, but it's the edge case where you can use an envelope detector. Any gain that is larger than k, that means you must use an envelope, you must use a coherent detector because you are going below the horizontal axis now. Okay, so E, because gain is now 2k, therefore we must use coherent detection, since 2k is bigger than k, and k gives us the edge case for envelope detection. Okay, so the basic block diagram would just simply be this. Like, it's just you have a signal coming in. Okay. Cosine, then 2 pi fc, and then the output. You have a low pass filter, and then you finally have your message signal within some tolerance, some scale factor. Okay. So that's what I would do. You'd have to use a coherent detection now. You can't use an envelope detector anymore because you're specifying amplitude that is beyond the maximum value, which means that you're going to get phase reversals. So you're going to unfortunately need a coherent detector. Okay. All right. Any questions here? All right. There's actually one more part to this question. Ugh, it's actually quite long. So I've only got 3 questions, so hopefully I should be able to finish the other questions by 10 or 15 minutes. I realize I've gone a little bit over time here because I was busy explaining stuff. So let h of f be the frequency response of a bandpass communication channel shown in figure 2, which is this guy over here. Oopsie. Undo move. Let me just scale this down. Okay. So we have this. So we have some, so what we're doing is we are taking our amplitude modulated signal and we're going to put it through our bandpass filter. So we actually are doing this. And we're putting it through a bandpass filter. And then we're getting some output. And then this bandpass filter is this guy over here. Okay? So what we have to do now is we have to figure out what the original message is. We have to figure out what y of t is. And then we have to figure out whether or not we can recover the original message from the output of the bandpass filter and explain and justify your answer. Okay, that's totally fine. Okay, so if you remember what the original message signal was, it looks something like this, right? So m of f, and it looked like this. So 1, 2, 1, 2. So this was 1.5. Okay, so this was minus 4,000. Actually, no, I'm not the original. It's the amplitude modulated signal, right? So sorry, let me cut that out. So it's actually, sorry, it's this guy here. So we had 1 at 50. So this was 2. This is 50, and then, oh, sorry. I have to draw the actual amplitude modulated spectrum, not the original message. So this is 46, 48, 52, 54. And I believe this was 1/4, 1/2, and 2. Okay, so that's what this is. All right, so what we need to do now is you have to figure out what the original message is. So this is the amplitude modulated spectrum. I'm just showing the positive only. Okay, and then I have to pass this through a filter, and then I have to see what the actual output is. Okay, so so let's actually go case by case here. So at 46 kilohertz, what I have here is I have some phase. So actually what's happening here is that we see that there's 2 lines. So there's one line here that's slope of minus 2 pi t naught. Okay, t naught is some constant which we don't know. And the output here is the slope here. So what's actually happening here is that, remember, this is a constant phase, right? So this is the slope. So the phase in this particular portion would simply be minus 2 pi omega t naught. And then this here will be minus 2 pi omega t of 1. They're telling you that the slope is constant. So that means that the actual phase itself is linear. Okay, so that's what's happening here. So there's actually 2 different phases that are going on. So what we need to do now is we have to figure out, we pass it through this filter, we see that there's magnitude and phase that have to be applied, and then we figure out what the inverse would be. Okay, so let's see what the original spectrum is first. So at y of f, so at 46 kilohertz, okay, we see that there's a gain of g, and then there's a phase of this slope here. Okay, so this means that we have, let me see here. So we have half g. Okay, delta f minus 46 kilohertz. Okay, and then there's also an impulse on the other side as well. Okay. okay? And then each of these are phase delayed by e to the, not e to the minus j, but yeah, it would be, let me see here. So there's phase involved. So you have e to the minus j, 2 pi, and then, actually it's not factored, I'm sorry. So you have this guy here. Let me move this over, sorry. Over this way, like that, okay? So you have e to the minus j, 2 pi, 46k, and then t naught, okay? And then we have the same thing here. And then we repeat this, you know, for multiple times here. So we have half, and then we have 1/4. Actually, I'm just going to copy this twice. So we have this guy, copy. Okay, so we have plus, and this half becomes 1/4. 4, 4, and this is not 40, yeah, 46, and then we have 48, okay, 48, and this is 48. And then, you know, so on and so forth, right? So there's one here, and then we have plus, you know, 2g delta f minus 50k, okay? And at 50, we have t of 1 as a delay instead. So e to the minus j 2 pi, 50k, t of 1, and then so on and so forth. T of 1, sorry. Okay, and then there's 2 more that I have to write out. So let me just copy this again one more time. Sorry, this is a little bit long here. Okay, copy this. It's going to go to the next page now. This is actually a midterm question from a long time ago, which I didn't write, of course, but so plus, okay, and then let's see here. Copy this out. Okay, so then there's 2 more, okay? So we have 52 and 54, so 52 and 54. 52, 54, 52, 54, and then 52 and 54. 52, 54, 52, 54. Okay, so we have one of those. Let me see here. Half and a fourth. Okay, so that's what's going to happen here. Okay, so now I need to figure out what the original time domain signal is. I'll just write it out partially because I'm running out of time. I want to be able to finish everything. But, okay, so if you take a look here, I have 2 impulses, right? And then I also am phase delayed by this much, okay? I'm actually phase delayed by, actually it should be actually, let me just double check here. Plus, oh, I see. Let me see here, phase, yeah, that's totally fine. So we are phase delayed here by, you know, by that as well. So what you do is these 2 impulses become, you know, a cosine. So this becomes g cos, and then 2 pi times 46,000. Okay, and then t, and then minus 46k is the delay. Actually, no, it's not 46k. It's just t naught. That's what the delay is. So if you remember what the Fourier transform property was, e to the, let me see here, x of t minus t naught. Okay, if you take the Fourier transform, it's x of f e to the minus j 2 pi f t naught. Okay, so both of those together will give you one phase shift of t naught and t1. Okay, so let me see here. Sorry, this is long. I wasn't expecting this to take long. So, k t1. Okay, so we have that. Okay, so let me just, we have that here. So t naught. Okay, and then plus, what we see here, g over 2 cosine 48k times 2 pi t minus t1. Okay, and then let me just brush this off over here, and then I have one more. Let me see here. So I've got 2, so this becomes 4g cosine of 50k times 2 pi t. Okay, and then we have two more. So G, what was this? Over 2. So we got G cos, not F, but 52K times 2 pi, and then T minus T1, and then G, which is over 2. Okay. Yeah, that took a little longer than usual. Okay, so that would be the final. That would be the final one. Okay, so the last question asks you, okay, so determine y of t. Can the message, where is it? Can the message be recovered? Why? Okay, well, I can tell you right now that it can't. If you remember, this talks about distortionless transmission. So if you remember what distortionless transmission was talking about, when you put a message through a channel, right, the output would be the message all delayed by some constant T naught, okay? If you take a look at each one of these, we'll see that each one of them is delayed by different ones. So we have T naught over here, right? There's also T1 over here, and then there's no shift over here as well. So because all these are being delayed by a certain amount, they're not all being delayed by the same amount, this would actually be a distortion-filled channel, which means that you actually can't recover your signal. So because all components are shifted by different amounts in time, therefore we can't recover T. Not M of T. Okay? Yeah, this is probably one of the harder questions. I will probably not ask you something like this. It's just too long and involved. But that's what you have to do. Okay. The next two questions shouldn't take long. It should take maybe about a couple minutes, not a couple minutes, but about 10 minutes, and hopefully I'll be able to let you guys go early. Okay. So next one. Okay. So this is the second question I got. Okay, so we have a message signal and a message signal, but we have an input signal that is a cosine wave of some frequency, which is 2 kilohertz, and then it's sampled by a periodic pulse train. So instead of using an impulse train, we're going to use a pulse train to sample the cosine wave instead. Okay, so this is what's known as S of t, and it's a rectangular pulse of tau seconds. So that means that the width is tau, and it's centered at the origin, and then we sample by TS intervals. Okay, so this would be the sampling time, which makes sense. Okay. We also know that the Fourier transform of this is simply a summation of impulses, where this is actually a property where you can, this is the Fourier transform of the Fourier series. Okay. Also, we know that the Fourier series coefficients are simply that, but there's a note here. You don't need to evaluate the coefficient values, you just have to represent them in terms of S, which is totally fine. Okay, that's great. Okay, so here's the next part. QB. Okay, so this is the first question. So if the sampling frequency was 5 kilohertz, draw the spectrum of the sampled output between plus and minus 10 kilohertz, and then repeat the same for 3. Okay, that's totally fine. Actually, no, sorry. Let me get this in black. Okay. We know for a fact that this here, right, this provides 2 impulses at plus minus 2 kilohertz and sampled, well, not sampled, but the height is going to be 1. So plus, this is 2,000 and 2,000. Okay, so that's actually nice. So actually, before I do this, if you remember, the sampled spectrum, right, is simply the convolution of the original spectrum with the sample one, right? Because this comes from the time domain, where if you actually multiply the 2 signals together, when you do the Fourier transform, it's simply the convolution, okay? So if this is my signal, then I convolve this with the impulse train. This is already given to us, so delta F minus F of S, okay? The output would just simply be copies of the spectrum of the original input that are scaled by the Fourier series coefficients. So X, F minus F, N. Sorry, there's an N here. Okay? All right, so we don't actually have to compute what the actual S values are. We just have to go ahead and just put them into the actual graph. Okay, so remember, you're sampling by, so this here would be 5 kilohertz. Okay, so at multiples of 5 kilohertz, I should see copies of my spectrum. Okay, so this is kilohertz. This is F. So if you remember, so we had plus minus 2. So this is what happens here. So we have minus 2 and 2 here. Okay, and then this here, this is when n is equal to 0. So in this case, this gets scaled by S of 0. Okay, now we're at 5, right? And then remember, it's you're taking your spectrum and you're copying it over by multiples of the sampling frequency. So you have to go plus minus 2 from here. So this is 3, and this is 7, right? So this gets scaled up, and here is n is equal to 1. So this is S1, or sorry, S minus 1, and S of 1. Okay? And then there's another one here, but then I technically have to go over by 2, so this would be 12, but we don't consider that because we only want to draw between plus minus 10. So then you go over here, which is 8. So then this here would be S of 2 minus, and then here would be S of 2. Here would be n is equal to 2. And then you repeat the same processing on the other side. So we have minus 7 and minus 3. So we have 1 and then 2, right? Actually, sorry, not this. This is just S of 1, not S of minus 1. So both of these are S1. Both of these are S2s. Okay? So here would be n is equal to minus 1. So S of minus 1, S of minus 1. And then finally, you draw 1 over here. And this would be S of minus 2. And then 1 over here, I guess, if you wish. But we don't consider this. So okay, so that's what the spectrum would look like. Okay, so that's for 5 kilohertz. And now repeat the question for 3. So because, remember, the sampling frequency was, so remember, the fundamental frequency is 2 kilohertz. So if you want to do sampling, you have to do twice the bandwidth, which is 4. So 3 kilohertz is actually less than the Nyquist frequency. In this case, it's 4 kilohertz. So you're going to get some aliasing, okay? So this is what happens when you do it for 3. So what's going to happen is that you have 0, and then you have copies at every multiple of 3. So we have 3, 6, 9, and then minus 3, minus 6, minus 9. All right? So at the very beginning, so this is minus 2, this is minus 2, and then this is kilohertz, right? This is F. So we have these two here, and then these are both S of 0 from the Fourier series coefficients. And then finally, at n is equal to 1, right, we have plus minus 2. So we're going to have 1 here and 1 here. So here and here. So this is S1 and then S1. All right? And then at 6, we have to go plus minus 2. So we're going to have 1 here at 4 and then here at 8. Okay, so S2 and S2. And then at 9, okay, let's do this one. So we have 1 at 7, and then 11 we don't draw. So this is S of 3. And then 11 here, this is S of 3. Okay? And then you do the same thing on the other side. So on minus 3, we have impulses at plus minus, plus minus 2. So we'll have minus 1 here. So this is S of minus 1. S of minus 1. Okay? And then again at 6, so we have to go minus 8, and then minus 4, 2, and then 2. And then finally, and then 3 would be 7. Actually, not 7. So 12 would be, oh, I'm sorry. At 9. Yeah, 9, so that would be 7 and 11. Okay, that's good. So minus 11, and then 7. So this would be S of minus 3, and then this is S of minus 3 as well. So that's what's happening here. So you can see that in comparison to the top, you see that the spectrums are evenly spaced out. With the aliasing, what's happening here is that they kind of mix with each other. So if you wanted to successfully get your original signal back, you want to get these two impulses at minus and plus 2, but there's also minus 1 and plus 1 that's interfering with things. So you won't be able to get your original message back, unfortunately. Okay, so I did that already. C. All right. I'm almost done here, guys. Thanks for your patience. But okay, so we can recover the signal up to a scaling constant from a sample version by low-pass filtering. So with an ideal low-pass filter, with a frequency response of a rectangular pulse that is, plus minus the sampled frequency. So basically it's going to look like this. So minus Fs to Fs. Okay? So if you let the sampling frequency be 5 kilohertz, use the result from part A to determine y of t. So if you take a look at part A, right, it's right over here. And okay, so let me just copy this. Copy it over. Sorry. Here. Okay, so this is this guy. All right, so this is part C. And this is telling us that our low-pass filter, right, if Fs is equal to 5 kilohertz, this means that we have to span between minus 2.5 and 2.5 kilohertz, because that's what the definition of the rectangular pulse is, right? So if I do this, and if I center this over here, so it looks like it's going over here, right, then that's my filter result. So after your low-pass filter, this is what I get. So these are my 2 impulses, right? So my final output would simply be 2 SO cosine 2000 times 2 pi t. Okay, and that's fine because this is our original signal, but it's scaled by some constant, which is fine. So that would be the output. So this would be the, I guess, y of t. Okay. Now, if you take a look at part D, if you do the same thing, right? I'm going to copy this spectrum and then put it downwards here. So let me just copy this. Copy. And then, sorry, here we go. Okay, so this is part D. My low-pass filter now is, because the sampling frequency is 3 kilohertz, right? I got to span between minus 1.5 to 1.5. So here we go, right? So that means that if I take this low-pass filter, I have to put it over here this way. Okay, so that means that my signal is actually going to be 2 times S of 1, right? So it's, sorry, it's S of 1 and then S of minus. Yeah, so it's just S1, I guess. Then also the fact that, oh yeah, I should probably point this out. That, where is it? Where is it? Oh, I don't know where that actual fact is. That's fine. So actually, because this is symmetric, right? S of minus 1 is equal to S of 1 because it's symmetric. Because that's what the sync gives us. So this actually becomes 2 cos and then 2 pi times 1000 t. So it's no longer the original message anymore. It's actually the frequency divided by half. And that's totally fine here. All right. Okay. So, all right. So we've got that. That's good. All right. So I've got one more part here, and then one last question. Shouldn't take very long, I promise, and then we'll get out of here. Sorry to keep you here until 9, but I figured, the more questions you do, the better shape you'll be for the midterm, I think. Okay? So sorry to keep you here for so long. So, okay, here's the last question. Actually, no, I just did this already. This is part D. Okay, here we go. This is the last part of this question, so this is E. All right, so what we're going to do now is we're going to change the signal up a little bit. So instead of it being just a, strictly, band limited signal, we have a non-band limited signal now. Okay, so we're going to take this guy and we're going to put it through this system. So what we need to do here is we have to design what's known as an anti-aliasing filter so that you minimize all these components that are strictly not band limited. So we want to cut this off so that you want to make sure that you do get a band limited signal as much as you can. So you want to design a filter such that you get rid of all this stuff. You just want these parts here. And it's subject to the following specifications. So the sampling frequency is 30 kilohertz, okay? And you also have to make sure that the maximum attenuation over the frequency band of interest is limited to 1 decibels. So that's what's known as the pass band. So this is the pass band. Okay. Also, the maximum attenuation for the aliasing components within the frequency band of interest should remain below 60 decibels, or this is minus 60 decibels. And then we have to sketch what this response looks like. Okay. So when you actually sample this, okay, so what's going to happen is that you have some, something like this. Okay. So this is one copy. Okay, this here is minus b of x. This here is b of x, okay? And then we're going to have some copy later on down the road over here that is centered at f of s, and then it's going to look like this. So, like that. Okay? All right. So at this point here, sorry, not that point here, sorry. It's between here and here, right? So this point over here, this here is f of s minus b of x, right? And then this here is f of s plus. So it's right at this point here where things start to alias. So this is the aliasing part, I guess. Okay? So you want to design a filter such that it looks like this. Okay, so you have f, okay? And then between 0 and the, what is it? 0, maximum attenuation with frequency band of interest. So you want to make it such that from 0 up to the bandwidth of interest, okay? The 0 dB, this is 0 dB. Okay, so you have, you know, something concentrated here like this, all right? And then up to, so what's happening here is they want you to make sure that anything in between the alias components, so between b of x and f of x, right here, that should be attenuated as much as possible. So the gain down here is minus 60 decibels. That's what they want. So it's going to look like that. So it may, you know, the filter may look something like this. So it may look like this, and then you want to go down, and then something like that. So that's what they want. So they're saying that in the pass band of interest, so between 0 and b of x, you want the gain to be 0 decibels, or, you know, 1 volts to volt, and then you want it such that you know, the aliasing parts, you want to make sure that what is aliased after this point, so this is actually, you know, between here and here is aliased. You want to make that attenuated so that the gain is 60 decibels. So that's you know, that's the thing that they want to look at. So this may be one shape, but the actual filter specification, so what, you know, the boxes here are what actually we're trying to look for. Okay. All right. So what? Okay. All right. So I'm actually almost done here, guys. Sorry to keep you waiting. So this will actually hopefully take about 5 minutes. So, okay, this is the last question. So 3. So we want to take a look at double sideband suppressed carrier modulation. All right. And let me see here. So let m of t be, you know, let me just get the actual question itself. Okay. So here we go. All right. So in this problem, we want to investigate double sideband suppressed carrier modulation. Okay. And we have the spectrum that looks like this. Okay. And then what's happening here is that we are going to use a let's see here. We're going to use a arbitrary periodic waveform instead. So instead of using, you know, a cosine wave, we're just going to use an arbitrary periodic waveform. So we're going to perform multiplication, and then we're also going to do a bandpass filter instead of a low-pass filter. Okay. So the first question here is, using the properties of the Fourier transform, determine what this would be, what the Fourier transform of that output would be. Okay. Well, m of t cosine 2 pi f naught t plus phi. Okay. Well, you can actually break this up into a, you know, a sum of two exponentials. So this becomes m of t. Then we have 1/2 e to the j 2 pi f naught t, and then this becomes e to the j phi. Okay, and then plus e to the minus j 2 pi f naught t, and then e to the minus j phi. Okay. The reason why is because you can consider this as x, and then, you know, cosine of x is equal to 1/2 e to the jx plus 1/2 e to the minus jx. And because we have a addition of both, you can split this up and make that, you know, a multiplication of the two bases. Okay? So now that we have this, okay, what we can do is we have two properties. So if you wanted to take the Fourier transform of this, notice that this and this, they are modulations, right? And then this is just a constant by itself. So if you wanted to take the Fourier transform, we get 1/2 m of f minus f0, and then this is just a constant, e to the j phi, plus 1/2 m of f plus f0, e to the minus j phi. These are just constants. They don't affect anything. And that's it for that. All right. So that's the first question, first part. The next question asks you, okay, so we have some, you know, periodic waveform that can be represented by this Fourier series, okay? What they want you to do is, okay, so let me see here. So we have complex valued Fourier series such that the coefficients have some gain factor with some phase, and then so this was represented by the magnitude and the phase. Okay, that's totally fine. So what they want you to do here is they want you to design a bandpass filter where the output will be such that the carrier frequency is centered at 150 kilohertz and the bandwidth of the message is 10 kilohertz. So what they want you to do is, because this is sampled, you're going to have copies of, so this here would be the fundamental frequency of the wave. So this is 50 kilohertz. So this 50 kilohertz is the frequency of S of t. Okay? So they have this, and then what they want you to do is they want you to make it such that the output will have your original spectrum shifted over by 150 kilohertz, and then this is minus 10 and this is 10 kilohertz. So they want you to figure out a bandpass filter that'll do that. Okay, that's totally fine. So B. Let's see here. Yeah. All right. So if you wanted to get it at 150 kilohertz, okay, what this is saying is that this would be 3 times 50 kilohertz, right? Or this is 3 times the fundamental frequency, F naught, okay? So remember, when this is, because you have a periodic waveform, when you take the Fourier transform, right, you're basically, when you're doing the multiplication, you're performing convolution here. So what's going to happen is that when you put a bandpass filter centered at 150 kilohertz, you're actually grabbing the third coefficients, okay? So what's happening here is that you're basically designing a filter such that it's centered at 150, okay? And this is, you know, minus 10 and then 10K here. Okay, so they want you to design a bandpass filter that'll actually get that. So we know what the fundamental frequency is. So it's just 3 times F naught. So therefore, the coefficients would be S3 is what we want. And then we also know that this is symmetric. I'm almost done. Only a couple more minutes, okay? So I need S of 3. Don't worry, trust me, it's only a couple minutes. I've only got like one last part to do. So once you have this, okay, so what you need now is you have to figure out what the, this, we have to represent the Fourier transform of this. So this is what we need to get. So double sideband express carrier. Okay. I need to concentrate on the third copy, which is at 3 times omega naught. So I need S3. Okay, and then I also need 1 here as well. So plus 3 omega naught here, 3F. Okay, so if you remember, these coefficients have some phase associated to it. So you have K3 e to the j phi 3 plus K3 and then e to the minus j. Okay? All right, so if you actually use Fourier transform properties, okay, what we can do is we can, so this is, so we have the, the time shifting, right? So if you just go backwards, okay, this becomes 2K3 cosine 2 pi and then 3 F naught t, and then this is phase shifted by pi over 3. Not pi over 3, but phi 3. Okay, so we're going backwards here. All right. Okay, last part. We're almost done. All right, this is only gonna take like a minute here. Let me just. Where's my mouse? Come on. Okay, here we go. All right, last part here, guys. So what we have to do now is we have to use a coherent detector so that we can demodulate and get the original signal back. So what we have to do is you have to figure out what exactly this is going to be, as well as what the low-pass filter is going to be. Okay, well that's actually pretty simple. All you have to do is you just have to make this cosine of 2 pi, and then this is 3F naught t, right? You have to make that the local oscillator beams. You have to make sure that this and this are matched, okay? And then the low-pass filter is very easy. All you have to do is just make it so that this is centered between minus B of M and B of M. Okay? And then you have to make it such that, you have to multiply by gain to get the original message back. Okay? Well, that's actually pretty simple. So when you apply the low-pass filter at this output, right, remember you're going to get 2 copies. You're going to get K3 M of t and then plus K of 3 cos. And then, 2 pi 3F naught t plus phi of 3. And then this goes away after the low-pass filter, right? So what you're left with is this guy. So you need a gain of 1 over K3 to get M of t back. and that's it. Okay. So there you go. So that would be the passband. So this is the passband. You'd have to make this the oscillation frequency, and then the gain would be 1 over K3 to get the original MOT back. Okay, sorry to keep it this long. Okay, I'm actually done now. Okay, so when you so I'm actually done in terms of AM. So next, so let me see. Actually, we're going to cover some more topics. So next class, we're going to talk about the super heterodyne receiver and some more receiving technology, and then I'll cover more of AM in terms of the tutorial next week. So thanks for coming out, and I'll see you next week.